Alright, this video focuses on transforming nonlinear data. So when a straight line is not the best mathematical description of a relationship, one can transform one or both variables to make the association more linear. When a nonlinear model will fit the data better, the residual plots reveals a pattern of some kind. Note that the value of r squared or r is not sufficient for assessing the fit of the linear model. So here's some examples of different transformations that can be done. The square root original function, that pattern, y equals the square root of x, we can transform it by squaring the y's. So what this does is just straightens that data out. It straightens the square root out. Same thing with the quadratic. To undo at x squared, we're going to take the square root. And then logarithmic, where we take the log or natural log of the x variable. The most common, however, transformations are the power and the exponential, and that's what we're going to focus on. So in a power transformation, we take the natural log of x and the natural log of y, or the log of x and the log of y. This is just changing our basis. And then an exponential, we're going to transform just the y. We're going to take the natural log of y or the log of y. So now you should run both of these, because when given a snippet of a graph, you can't really tell by looks alone whether it's going to be power or exponential. So here's an example. First of all, let's look at just some basic algebra about solving, because one of the favorite multiple choice questions are going to be solving exponential and log transformations. Alright, so in this case, alright, remember our base is e. So if I rewrite using the definition, I'm going to get y is equal to e to the ax plus b. So look at the following example. So base of e here. So y is going to equal to e to the 4.67. Let's let x equal 3. Because we're trying to make a prediction when x is equal to 3. So we're going to plug in 3. Well, because of technology, I can just plug that equation into my calculator. So if I go to e and type that entire expression into my exponent. So that's what my prediction for y. Pretty big number. Alright, and here's the power transformation. So here again, base of e, if I rewrite using the definition, y is going to equal to e to the ln natural log of x plus b is a general form. And then if I want to write, let's let x equal 2 here. So I'm going to write it, y is equal e to the 0.567 natural log of 2 minus 7.2. And I'm going to put that in the calculator. So here again, pull up e and type that in. So 0.567 natural log of 2 minus 7.2. Alright, so there's my prediction for y. Alright, so what does a problem look like? Alright, here's an example. This is data that shows the relationship between the f-stop of a camera's lens and its shutter speed. We're going to use our independent variable, our explanatory variable, shutter speed, and our response variable is our f-stop. And eventually we're going to use, whatever model we decide to use with this, we're going to predict the f-stop for a shutter speed of 1/4. So what I originally did is you want to run linear regression on this thing. Or plot, first thing you want to look at is a scatter plot of the shutter speed versus the f-stop. See that curve? All right. And then when I did the residual, so I run regression. My r and r squared values are good, so there's like showing me nothing wrong. But when I go to look at the residual plot, I see that pattern. That's what's telling me that I shouldn't have done linear regression here. So I'm going to try to straighten out this data. All right. This pattern looks somewhat logarithmic or exponential. So what I decided to do here through trial and error is I found that a power transformation worked the best. So you take the natural log of x, which is the shutter speed, against the natural log of my f-stop. And I ran my new regression. Notice that the r squared and the r values got better, and the more importantly is that the residual plot no longer has a pattern. Now, when I go to write this equation, because this is a transformation, I've got to include these transformations as part of my final equation. So when I write this, I'm going to go the natural log of my y, which was my f-stop, is equal to my a times the natural log of my shutter speed very not straight here, plus my b. So the biggest mistake that people make on this is the fact that when you do that transformation, you can no longer write it in terms of just the original variable. We have to include that transformation. All right, let's look at the worksheet you were given. So we're going to start off with, we have age in years, and then we're going to try to predict the income based on age. So the first thing you want to do is draw a scatter plot. So enter a calculator. We're going to go to Stat, Edit. If there's anything in your list, you want to clear them out. And our age is our explanatory variable. So we're going to just type in our x values. And then our corresponding, now this income is in thousands. This data is a little old, so it hasn't kept up with inflation. So the first thing we're going to do is run linear regression on this, because it's kind of like our baseline. We've got to figure out where we're starting from. Alright, so here's my original data. So what I want to start off first is I'm going to look at a scatter plot of this data. So my equals, turn it on. Alright, pick the scatter plot, defaults to list 1, list 2. Make sure my y equals are empty. I notice that my second stat plot is on. I'm going to turn that off because I don't want anything competing with my data. Alright, so now I'm going to zoom 9. Alright, I can see a curve. Alright, so I'm going to, like I said, this is my baseline. I'm going to run linear regression on it. Alright, so I'm going to run linear regression on this to get a baseline to compare my transformations to. So I'm going to go Stat, Edit, Try that again, so I can quit. I'm going to go Stat, Calc, Linear Regression, List 1, List 2. And there's really no need for me to store it in my regression equation because I'm not going to use it. I know that this is not going to be the best fit. So I'm just going to calculate. All right, notice my R and R squared are not showing up. I really need those, so I'm going to turn those on. So I'm going to go to Second, Catalog, hit the D for, and I'm looking for Diagnostics On. Hit Enter, Enter again, and now I'm going to rerun linear regression. So Edit, or Stat, Calc, Lin Reg, and I'm going to calculate again. Alright, so this time I'm getting my R and R squared values. Notice they're both good. Alright, so that's my baseline. Like I said, I'm going to write down that R value just so I have some comparison. So let's write down that R value of 965. So my goal is to make that better. Alright, so now here's the true test. I'm going to look at the residual plot. Remember, I don't want a pattern. So I'm going to go back in here, Stat Plot, and now typically when I make a residual plot, I plot it against the predicted Y values, but here I'm just using this as a quick check to see if it's fit. So I'm going to leave it in list 1, but I need to change my Y list to residuals. That's what's important. You can actually make a residual plot against anything in your X list. Alright, so I'm going to pull up resids. I'm going to rezoom it, zoom 9, my equation. And notice that pattern. That's what's telling me that it's not a good fit. Alright, even though my R and my R squared values were high, close to 1, this pattern in the residual plot makes everything bad. So I'm going to try to straighten this out. So the first thing I'm going to do is I'm going to go back into my stat edit, and I'm going to transform. I'm going to start with a power transformation. So in a power transformation, I'm going to take the natural log of age and of my x and a natural log of my y. So I'm transforming both. Alright, so back to the calculator. So go over to list 3. I want to take the natural log of list 1. And then in list 4, I want to take the natural log of list 2. I'm just trying to straighten this data out. And like I said, this is trial and error between the two of these. See which one works the best. Alright, so now when it's rerun linear regression, but now I'm going to run it on list 3 and 4. Here again, I don't, I'll come back and store it or write it down. Right now I'm just going to calculate to see if I got any better. Well, my R and R squared values got better. Okay. Now, here's what, like I said, I want to take the time to write down the equation for a moment because this is where people mess up. So if we had, so once I ran this, get both of this to show up at the same time so I can write these down. Alright, so my R value is 0.987. Alright, now here's what I'm talking about. Because I transform both of these, I have to include those transformations in my equation. Because what you're going to want to do is write income and age, but it's no longer, we've transformed it. And these are predictions, so we should put a hat on it. Okay, so what was my A value? 1.782. the natural log of age, and my b value is negative 2.578. All right, more importantly, okay, R did get better. Let's see what the residual plot looks like. So here again, I'm going to go in here. I've rerun regression. So this is my latest residuals in here. Like I said, this X list really doesn't matter. You can change it to list 3 if you want to. You can leave it and you can see that you get the same thing. What's the most important part is that the Y list is the residual list is the most current one, and it's in the Y list. All right, so I'm going to zoom 9 this again. And you see there's very little change in my residual plot. There's still a definite pattern. It's starting to flatten out a little bit, but there's still a definite pattern. So a power transformation is not the way to go. That's what this is showing you. All right, so even though a power transformation made it straighter, our R value got better, this is a bad residual plot. So it's still not, we're still not where we need to be. All right, so let's try an exponential. An exponential transformation leaves the original age alone, but we're going to take the natural log of the income. So remember, this was in our list, so we're going to run list 1 against list 4 when we do our linear regression. Heavy, heavy on the calculator. So we're going to go stat, calc, linear regression. I'm going back to list 1, and I'm leaving my Y list as list 4. All right, calculate this. Notice my R and R squared values got even better. But the true test is that residual plot. So when I go to look at my residual plot, here again, I can put anything in this. If I want to go back to list 1 because that's my X's, that's fine. I'm going to rezoom it. See, my pattern has gone away. It's going back and forth on either side of 0. This point might have a large residual. This one has a rather large residual. All right, so there's possible outliers. All right. And if I look at let's go back and look at, so the residual plot's good, and you see that when you look at the scatter plot, all right, my data is very straight now. So this is the age and the natural log. All right, so my R value got much higher than my original baseline. Remember, it was 0.965. Now we're almost at 1. It's almost a perfect fit. All right, here again, notice the equation. It's the natural log of the income, and it's a prediction. And then I've got my A rounded to 3 decimal places plus my B. Now, I did not transform my age. All right, so this is good because no pattern in the residual plot. That's what we're looking for. So we've decided that the exponential model is the best fit. So now I'm going to use this to make my predictions. So my question is, all right, use the model to predict the income of a 36-year-old. So what we're going to do is we're going to take that 36 and we're going to plug it in for our age. All I did was simplify and got value to 3.702. Use my definition and rewrite. So income is going to equal to E to 3.702, which is 40.5283. But remember, we're in thousands. So we're going to multiply that times 1,000. So that's the predicted income for a 36-year-old. All right, use technology to find the model. All I was saying here is, so this, since we decided this was an exponential model, in our calculator, we can actually run exponential regression. Now I'm going to do this on my original data, list 1, list 2. So if I go into Stat, Calc, I go down near the bottom, there's all the different quadratic regression, there's logarithmic regression, there's exponential. So all it's going to do, now make sure you run it on the original data, list 1, list 2, it's going to write the equation in exponential form instead of being so it's going to solve for y. All right, see that we're getting the same r value that we did before. So this is the exponential equation. Now you're typically not asked to do that. We're more interested in being able to straighten out nonlinear data than actually using technology to get the exponential equation. So what I'm saying is it's probably going to be left in this form. All right, here again, the biggest mistake that people make is when they transform, they don't include that as part of their original or the final equation. So you're trying to straighten out the data to get rid of the pattern.